Okay, let's look at the first problem. For a short period of time, the motor turns gear A. So gear A is the driver and it's connected to the motor with a constant angular acceleration of alpha A 4.5 radian per second. So this one is constant. So we can use the equation that are based on constant angular acceleration. Starting from rest. Determine the velocity of the cylinder and the distance it travels in 3 seconds. So we want to find the velocity of this cylinder. The velocity of the cylinder is the same as the velocity of point P prime that is shown here. And the velocity of a cylinder would be the linear velocity, but is related to the angular velocity of our gear B. If we know the angular velocity of gear B and we know the radius, we can find a linear velocity. The cord is wrapped around pulley D, which is rigidly attached to gear B. So we have 2 gears and 1 pulley. We are given alpha A 4.5 radian per second squared. We should start from rest. Omega A naught would be 0. We want to find the velocity of the cylinder, which we said that the velocity of cylinder is the same as the velocity of the point of contact. Also the distance that it travels, we can call it x. In 3 seconds, our time is 3 seconds. Because the 2 gears are in contact, we can use the equation for the gear between A and B. Alpha B over alpha A, they are inversely proportional to the radius. So RA over RB. Therefore, alpha B, RA over RB, so that would be 75 over 225 millimeter. I'm not going to change it to meter because it's going to cancel out. So I just write it in millimeter, 75, 225 times alpha A, which is given as 4.5. Therefore, alpha B is 1.5 radian per second squared. So if I have alpha B, if I have the angular acceleration, I can find the linear acceleration for this point. AP prime is RD, because that's the radius that I'm interested in, RD, the radius of the pulley, times alpha B. Alpha B and alpha D are the same thing because they're connected, they're on the same shaft. So alpha B is the same as alpha D. The pulley and the gear are rotating with the same angular velocity and angular acceleration. So alpha D. RD is, I'm gonna change it to meter here. So I have the correct unit at the end. Also alpha D, which is the same as alpha B, 1.5. Then I will get 0.187 meter. Let me write it here. .187 meter squared. So if I have the velocity, if I have the acceleration of this point, I can find a velocity. It's just a linear equation. So velocity is A P prime times T. I have this value, 0.187 time, it takes 3 seconds, so that would be 0.56 meter per second. And I didn't have any initial velocity. That's why the equation is very simple. It starts from rest. And now that I have the velocity, I have the acceleration, I have the time, I can find the distance that it travels. So x x naught plus v naught t plus half of acceleration t squared. Which acceleration? The acceleration of my point p prime. The initial is 0 for both. So the distance that it travels is 0.187. The time, 3 seconds. So I can find x, 0.84 meter. So that's the distance that it travels. I have the acceleration, the initial velocity is 0. I have the time. The question, in addition to the distance that it travels, asks for uh, velocity of the cylinder. We found the velocity of the cylinder and the distance it travels in seconds. So we are done with the problem. If the problem was asking for the angular acceleration, we could find the angular acceleration of the other gear as well. Now let's move to the second problem. So here at the instance omega a, 5 radian per second, pulley A is given a constant angular acceleration, alpha A, 6 radian per second squared. So we have alpha A acceleration, and that's constant acceleration. We have the initial. So let's write omega A, not indicating the initial radial velocity. Also, we have the acceleration, which is constant. We want to find the magnitude of acceleration of point B. So here, because we want to find the acceleration of point B, we have to remember that the acceleration has two components, one the tangential and one the radial one. So AB is AB, the tangential component, and also AB, the normal component. I just write it with UN and UT are just the unit vectors. The tangential component is R alpha. So A, B, T is R alpha, and A, B, N is R omega squared. So we are on gear B. We have RB here, alpha B here, similarly RB, omega B. So I need to find alpha and omega for gear B. I have for gear A, and if I write the gear ratio, I can find for the other gear as well. So I know the velocity here should be constant at these 2 points. So I can write the gear equations here, even though I have a rope connecting the two. So the gear equation is still valid. So omega C over omega A is R A over R C is inversely proportional. If I find omega C, RA is 50 millimeter. Again, I'm not going to change the unit here. RC is 40. And omega A, I don't have omega A. I need to find omega A. If I have omega A, I can find omega C. So let's go back to the question to find. We want to, we have the acceleration. We know that gear A is going to rotate 2 revolutions. So we have delta theta as 2 revolutions. 2 revolutions means 2 pi, so 4 pi. And I have the initial, I have the acceleration, I can find the final angular velocity. So here omega a squared minus omega a naught would be 2 alpha delta theta. So omega a, that's what I'm trying to find. Omega a naught, which is 5 squared, would be 25 plus 2 alpha a. Let's write the subindex a is 6 and then 4 pi. So I can find omega a here to be 13.25 radian per second. Now that I have omega a, I can plug it into the equation of interest and I can find omega c. So omega c is 50 over 40, 13.25 would be 16.57 radian per second. Having omega c is identical as having omega b because the two gears, the gear and the pulley, or the two pulleys are uh, connected. So omega b is the same as omega c. They are connected. So we can write the normal component of acceleration here now, r omega b squared. So r here is 0.06 omega b is the same as omega c, so that's 16.57, 1648 meter per second squared. So I found the normal component of acceleration. The other component would be r. Let's write rb here and rb here for alpha b. I have rb 0.06. I don't have alpha b. I have alpha a, but I can write the gear equations and find alpha b based on alpha a and the radius. So let's do that. Let's here alpha c. I write alpha c because that's what is connected to pulley A. But then at the end we'll conclude that alpha c and alpha b are the same thing. Is inversely proportional. So RA over RC, alpha C, RA is 50 over 40, and alpha A is 6. So that would be 7.5 radian per second. So now that I have alpha C, I can write here that alpha C is the same as alpha B because the two pulleys are connected. So alpha, I have alpha C, I can just plug it into my equation here. Alpha C and alpha B are the same, so 7.5. So that gives me 0.45 meter. So I found both components of acceleration, the normal component and the tangential component. I didn't have neither of angular velocity or angular acceleration, but I found it based on the information that I have for the pulley A. So now that we have both components of the acceleration, we can find the total acceleration. AB would be each component squared. I try to fit it here. So 16.48 squared plus 0.45. At the end, AB is would be 16.49 meter squared. You can see for this case, the majority portion of the acceleration is the normal acceleration. And the tangential acceleration did not have much contribution in the overall acceleration. So the important thing that you need to pay attention to is that here at this point, when acceleration is asked for, we have two components of acceleration and we have to consider both components of acceleration. Let's go to the other problem here. It's a similar nature. We have two gears in contact. We have information about one gear. We want information about the other gear. So we have to use the gear ratio. And motor A gives gear A an angular acceleration. So motor A would be our driver. I would like you to be familiar with these terminology that we use, driver and driven. Angular acceleration, so we have everything for gear A, we want for gear B. The acceleration is not constant, so we have to be careful. We can't use equation for constant acceleration as with constant acceleration assumption. So that's our acceleration for gear A. It's in second. If the gear is initially, so we have an initial angular velocity of 15 radian per second. Determine the angular velocity of gear B at time. So angular velocity of gear B at time 3 seconds. So there are multiple ways you can do it. You can directly relate the angular acceleration of gear A to gear B and then find the angular velocity, or you could find the angular velocity of A at this time and then write the gear ratio. It really doesn't matter which one you write first as long as you follow the gear ratio. So I want to find omega A, and then I write the gear ratio to find omega B. So omega A at t equals 3 seconds. That's the first thing that I want to find. The acceleration is not constant, so we have to be careful. We have to use the derivative equation. We know alpha is d omega over dt. It's better to write. So d omega dt, so d omega from omega naught to omega is equals to alpha dt. So here omega would be omega, writing for gear A naught equals alpha, which is 2, let me write it and then take integration from 0 to t. Now let's replace it, omega A naught is 15, would be 2 after integration. It's just simple polynomial. T here for us is 3 seconds. So solving that, I will get omega A to be 55.5 radian per second. Now that I have omega A at the desired time, 3 seconds, I can find omega B. Omega B over omega A is inversely proportional, RA over RB. So omega B RA is 100 over 175 times 55.5. Therefore, omega A or omega B here, 31.71 radian per second. So here, it was the same as other gear problems that you have information about one gear, you wanted about the other gear. Whether you take this derivative for gear A or B, really doesn't matter. I just stayed with gear A and found the angular velocity for gear A. And then once I found the angular velocity, then I used the gear ratio to find the angular velocity for the other gear. As I mentioned, you could move everything to gear B and then write the gear ratio for the accelerations and then take a derivative. So it really doesn't matter whether you take the derivative and write the gear ratio, or write the gear ratio first and find the acceleration and then take an integral. So it's up to you. You can use both methods to prove that both approaches would give you the same result. That would be for this video.